Hello, I am Caterina Viola, and in this video I will give an introduction to the paper The Combined BLP and Affine IP Relaxation for Promised VCSPs on Infinite Domains. This is a joint work with Viola Živný.
Consider the following problem, which is called free colorability. We are given a set of free colors, and the task is to color the vertices of a given graph so that two adjacent vertices have different colors. This is an example of CSP or constraint satisfaction problem. A constraint over a set D is an n-ary relation R over D for some natural number n. A relational structure is a couple A di sigma, where D is a finite set called the domain and sigma is a set of relations over D. Given a relational structure A di sigma, an instance I of the constraint satisfaction problem for A, or CSPA for short, consists of a finite set V of variables x1 up to xn and a formula psi, which is given as the conjunction of finitely many relations from sigma applied to some of the variables from V. An algorithm solving CSP of A on instance I decides whether there exists an assignment alpha for the variables from V with values in D that satisfies all the conjuncts, that is, an assignment alpha which makes psi true.
The CSP framework is very expressive. There are several problems arising from theoretical computer science that can be formalized as CSPs. Moreover, the notion of constraint satisfaction problem can be extended to capture many other interesting problems that do not fall within the classical CSP framework.
There are three extensions of the notion of CSP: infinite domain constraint satisfaction problems, or infinite CSPs, promised constraint satisfaction problems, or PCSPs, and valued constraint satisfaction problems, or VCSPs. In an infinite domain CSP, the domain of the relational structure is allowed to be an infinite set. The task of a promised CSP is to find an approximately good solution to an instance of a typically hard problem when a good solution is guaranteed to exist. Each constraint of a promised CSP has two relations, a strict one and a relaxed one. Finally, valued CSPs capture optimization problems. To model preferences, constraints are expressed by cost functions rather than relations.
Now I will give the formal definitions of infinite domains constraint satisfaction problem, promised constraint satisfaction problem, and valued constraint satisfaction problem, together with examples that motivate these notions.
Our first example is the acyclicity problem. We are given a directed graph, and the task is to find an ordering L of the vertices such that L of U is smaller than L of V for each directed edge U to V. This is an example of infinite domain CSP. Observe that for a particular instance of the acyclicity problem, that is, for a particular graph, the size of the domain is bounded by the size of the set of the vertices of the graph. However, we need to have an algorithm which works for every instance of this problem. This is the reason why we can formalize the acyclicity problem as a CSP only if we allow the domain to be an infinite set. In general, an instance of an infinite domain CSP is defined exactly as an instance of a classical CSP, except for the fact that the domain is allowed to be an infinite set. Clearly, the class of infinite domain CSPs strictly contains the class of classical CSPs. Our second example is free 5 coloring. We are given a graph which is known to be free colorable, and the task is to find a 5 coloring. This is an example of PCSP. A promised template is a couple AB of relational structures over the same set of relations sigma with domains A and B respectively, and such that the relational structure A is homomorphic to the relational structure B. An instance I of the promised constraint satisfaction problem for a promised template AB, or PCSP-AB for short, consists of a finite set V of variables x1 up to xn and a formula psi which is given as the conjunction of finitely many relations from sigma applied to some of the variables from V. So far, the definition of an instance of a PCSP is the same as the definition of an instance of a classical CSP. But an algorithm solving PCSP-AB on instance I outputs yes if there exists an assignment alpha for the variables from V with values in A such that psi is true in the relational structure A. And it outputs no if for all assignments beta for the variables from V with values in B, we have that psi is false in the relational structure B. Our third and last example is the mean vertex cover problem, in which we are given a graph and the task is to find a minimum size set of vertices W such that each edge has at least one endpoint in W. This is an example of VCSP. VCSPs capture optimization problems, and to model preferences, the constraints are expressed using cost functions. A cost function over a set D is an n-ary function phi with domain D taking values in Q union the set containing the symbol plus infinity for some natural number n. A valued structure is a coupled gamma d tau, where D is a finite set called the domain and tau is a set of cost functions over D. Given a relational structure gamma d tau, an instance I of the valued constraint satisfaction problem for gamma, or VCSP gamma for short, consists of a finite set V of variables x1 up to xn, an objective function capital phi which is given as the sum of finitely many cost functions from tau applied to some of the variables from V. Finally, we are given a threshold that is a rational number u. An algorithm solving VCSP gamma on instance I decides whether there exists an assignment alpha for the variables from V with values in D such that the cost of the objective function, which is defined as the value of phi corresponding to the assignment alpha, is at most u. Infinite domain CSPs, promised CSPs, and valued CSPs are three different extensions of the notion of CSP. In our paper, we took into account a combination of these three extensions. That is, we took into consideration the class of infinite domain promised valued constraint satisfaction problems, or infinite PVCSPs for short. I want to mention the fact that combinations of two of this extension have been taken into account in the previous literature, for example in the case of infinite domain VCSPs. In our setting, we are given a promised valued template, that is, a coupled delta gamma of valued structures over the same set of cost functions sigma and with domains D and C respectively. We assume that the domain D is a finite set and that the domain C is an infinite one. Let I be an instance of PVCSP delta gamma with objective function capital phi of x1 up to xn given as the sum for j running from 1 to q of the cost function phi j from sigma applied to the tuple of variables xj. The problem PVCSP delta gamma on instance I can be rewritten as the following integer program with variables lambda jt and mu xia. Let us take a moment to understand what is going on in this minimization problem. The variables lambda jt and mu xia are required to take values in the set containing 0 and 1. Having mu xia equal 1 corresponds to the fact that the variable xi is assigned to the value a from the domain D. Similarly, having lambda jt equal 1 corresponds to the fact that the tuple of variables xj is assigned to the tuple T of elements from the domain D. The second row expresses the fact that every variable has to be assigned exactly to one element from the domain. The first row expresses the marginality relation that has to hold between the lambdas and the mu's. Finally, we must have lambda jt equals 0 whenever t is not in the domain of the cost function phi j, that is, whenever phi j of t is equal to plus infinity. Solving an integer program is in general NP-hard. Therefore, we considered two relaxed versions of the previous integer program which are solvable in polynomial time. The two relaxations that we considered are the basic linear programming or BLP relaxation and the affine integer programming or AIP relaxation. These two minimization problems are defined exactly as the integer program that I showed you in the previous slide, except for the fact that the variables in the BLP relaxation are required to take values in the set of non-negative rationals, and the variables in the AIP relaxation are required to take values in the set of integers. We proposed an algorithm for promised VCSPs on infinite domains that is a combination of the BLP and the AIP relaxations. The AIP relaxation can be refined by removing the variables that correspond to the zero coordinates of a BLP solution. Our algorithm solves the refinement of the AIP relaxation with respect to a special solution to the BLP relaxation.
We would like to know which are the promise valued constraint satisfaction problems on infinite domains that are correctly solved by the BLP+AIP algorithm. We answered this question in terms of algebraic properties of the promise valued template.
More precisely, we have the following theorem. Let delta and gamma be a promise value template such that delta has a finite domain. Assume that for all natural numbers L, there exists a block-symmetric fractional polymorphism of delta gamma with arity to L plus 1, having two symmetric blocks of size L plus 1 and L respectively. Then, the BLP+AIP algorithm correctly solves PVCSP of delta gamma in polynomial time.
In the last part of the video, I will introduce the technical notions of fractional polymorphism and of block symmetry.
Let gamma and delta be valued structures over the same set of cost functions sigma and with domains C and D respectively. An Emery fractional polymorphism omega from delta to gamma is a probability measure on the set of maps from D to the M to C with non-empty support, and such that for every cost function phi from sigma and every choice of M many tuples from D to the arity of phi A1 up to AM, we have that the expectation for phi of G applied component-wise to A1 up to AM in gamma, where G is distributed accordingly to omega, is at most the arithmetic average of phi of A1 up to phi of AM in delta. An Emery fractional polymorphism omega is block symmetric if there exists a partition of the coordinates of G into blocks B1 up to Bk such that every map in the support of omega is permutation invariant within each coordinate block Bi.
This is everything I wanted to tell you. Thank you very much for your attention.